Okay, so we're now recording. So a few things to get started. We will be having two other webinars to kind of follow up to this. You don't have to attend the first one to attend the second one, or the second one to attend the third one, but they all are useful. So this first one is going to be kind of an idea of the kind of ways to maybe think about using computational resources in your research. And the following one on Wednesday at the exact same time, 10:30 to 11:30. We'll be covering basic Linux commands, basically figuring out how to be comfortable working with a Linux system, because that is the most common platform for computational research these days. And also pretty much all high-performance clusters are based on Linux, and learning these basic commands. So it's good for anybody who needs to work with a Linux machine, whether you're using a cluster or not. On Friday at the exact same time, 10:30 to 11:30, we will cover the final piece, which is stuff specific to using a cluster. We'll use Flux as an example, but stuff you learn there will translate to an NIH cluster, a DOE cluster, an Exceed cluster, an NSF cluster, an Insight cluster, all of those things. They'll pretty much work the same. We'll cover the basics of batch, how to submit jobs to a cluster and how to think about them, and how to use modules, which is the most common way to kind of manipulate your software environment on a system. Okay, but today, why would anybody ever want to use a cluster for computing? So we'd like to think about moving beyond a laptop. And it can be anytime you want to get computation off your laptop. So even if you're running only small cases that run for a couple of hours, if you've ever found yourself thinking like, man, I'd really like to take this laptop with me to this seminar to take notes, but you know something, it's 2 hours into a 4-hour run of R, I really don't want to disrupt it. That's the kind of thing that we think, you know, as soon as you hit that point, that's when you should start thinking about possibly using other resources. And so that's what we're here to help with, is to kind of point you to other resources, make the most of resources you have available, and things like that. So again, that email address, hpc-support@umich.edu. Send us literally any question you may have about using computational resources. Flux, your desktop, the stats service, anything like that. So when you want to move off. So why would you want to move off your laptop? One is disruption, which is what I kind of talked about you want to take your laptop with you to a seminar, so you want to not have the disruption of shutting it down, but you kind of have to take it with you. So if you use a dedicated resource for computation, this could be buying a dedicated desktop for your lab, or using a service like Flux where you can jump on, use our processors in batch, and you don't have to leave any type of connection open to it, and it will just keep running. So you can take your laptop with you. Your laptop is freed up to doing everything you want to do interactive-wise, while anything that takes a good bit of time run off. The most common thing people think of, probably why they would ever go, is they probably think like, oh, my workload is not big enough to take advantage of a cluster. I'm not one of those big 1,000 CPU things. Here's the deal. The majority of the people who use Flux as an example have allocations of less than a single node. A single node I'm using here denotes a dual socket 16-core machine. So it's a dual socket 8-core processor. So this is the same size as a high-end workstation you would put in your lab. This is a single server. Most people who are using Flux have allocations smaller than 16 processors. Yes, there are people who have a significant number of cores, and if you have a need to run a bigger case, this is either you need more CPU horsepower, or you need a bigger memory footprint, or you need a bigger disk for storing intermediate data or post-processing data. We can handle all of that, and we have places to handle things bigger than what we can do here. But anytime you want to do that, realize that the majority of people using this stuff could actually fit inside a single workstation. So there's other reasons they decide to use us. So of course there's the bigger case, one really big run. Well, think about anything in terms of time to solution. This is, you may think your runs aren't very big, but you may have a lot of them. Let's go back to that 6-hour R example. They may not seem like very much. 6 hours, when we talk about people running stuff for a month at a time, or using a few hundred processors. A single R case, it only takes a few hours, or maybe even only a few minutes. What the next metric is, how many of those do you have to run? you have something like a parameter sweep. How big is your parameter space? How many different permutations do you want to run? If a single permutation is only 15 minutes and you're focused on 15 minutes isn't very long, we have tools and resources to help you be able to run many thousands of cases. So if you only have, a few tens or a few hundreds, obviously our tools work for that too. And there's simpler tools and there's more complex tools. But the idea is if you have a number of small cases. So if you would think that something only takes 15 minutes, but you'd like to be able to search a larger parameter space, you want to do exploratory work, you want to touch things that are out there a little bit, well, using a system like ours where you have many processors available to you, or other resources, Open Science, Grid, Exceed, others I'll touch on in a minute, will enable you to be able to run many small cases simultaneously. It's not that uncommon for people to submit many cores worth of individual tasks independent to each other to our system and have them all run simultaneously. So the idea is instead of waiting for a 15-minute case to finish, 15-minute case to finish, 15-minute case to finish, what if you could run all your 15-minute cases simultaneously? So instead of 15 times the number of cases you have to run long to do, you can have many of these done at once. So that's the idea of running more. More is different than bigger. In the end, though, depending on your work, they're all bigger. So this is a perfectly valid use of a system. So that's actually a more common thing to work with. Turnaround time, that's basically everything I've been talking about. How long does it take for you to get some sort of meaningful result that you can make yourself? And I don't know if any of you guys are familiar with the book, The Ultimate Resource, where it talks about the human mind. That is the limiting factor in all these cases. Don't let computers be the limiting factor. Always have yourself be the limiting factor. And that will make you publish sooner. That'll make you publish more often. That will make you have higher impact, graduate sooner, depending if you're a faculty or a student or trying to get tenure or you're just curious about something. If you really are just that pure, I want to know why, we can enable that if it's anything computational based. Actually a common thing, if you know anybody who's an experimentalist, experimentalists are like, oh, this computer stuff isn't for me. Well, something, simulation, experimentation, validating experimentation. It's really a good idea for an experimentalist to team up with a simulation person. So you can put these together so they can be complementary. That said, if you can put together an experiment in a day and a simulation on a desktop takes a week, the simulation is not that useful, right? Because now you're waiting to see whether you might as well just run 5 experiments or something, assuming it's cost effective. Come to us, we can figure out how to speed up that simulation so it actually has a turnaround time to help you maybe guide the parameters of your experiment. See the idea of experimentalists and computationalists need to actually work together to move science forward, get more papers published, increase impact, and things like that. So it's a good idea to kind of work together. But if the simulation can't get done in a soon enough time, whether it's a bunch of cases you want to study, remember the parameter sweep, lots of small cases to figure out possibly the parameters you want to explore and experiment, or doing the larger case. So the whole idea is how quickly can you get stuff around. So that's really my entire justification. That is the entire intent of this discussion, is to point out that you can run large cases, you can run many small cases. They're all valid uses. As soon as you want to free up your laptop, this is when maybe you should start looking for other resources. Even before you want to free up your laptop, if you're curious about tools available or libraries available so you can avoid having to write stuff, what's the most popular tool for doing statistics based on economic data? Well, I can tell you right now, that's Stata, but R is growing. Most common tools for statistical data in the medical field probably is R right now, but SAS, SPSS, they're all kind of there. We have a lot of familiarity with this, so you can always ask us at this HPC data support. So I want to touch on, that's kind of like the generic benefits of moving to dedicated computational resources. I want to touch on Flux specific ones. So Flux has all of the hardware characteristics, and people get focused on Flux for that. But if you notice, I keep saying contact us. so we can give you feedback and guidance. Use us as consultants. And we're free. It's free to send in an email and ask us a question. There is no silly question. To leverage our experience, having seen a lot of different work. The Flux benefits are, the major one is the people available. When you send an email in to hpc-support@umich.edu, which is down there in the chat box, you will get myself, you'll get Dan, you will get specialists from the medical school, you get specialists from the public health school, you get specialists from the liberal arts school, you get specialists from the engineering school, you get literally everybody who focuses on enabling computational research on campus in a generic way. And if we can't help you, we probably know the person who can. So we're always a good starting point anytime you're going to embark on a computational need. Talk to us sooner rather than later so that you don't have a lot of sunk costs into something that maybe is suboptimal. And you can always come back and talk to us later. The second thing that Flux has that's kind of unique to other computational resources is one thing Flux comes with is a significant software library. So you may be thinking like, well, I'd like to run many cases of SAS, but you know something, I only have one copy of it, so I can only run one simulation at a time. Well, you know something, we already have SAS. We already have MATLAB. We already have ANSYS. We already have, Star CCM. We already have the genome tool chains installed. We already have all these things set up. And if we don't have it, well, let us know about it. And if we find out that there's demand for something, we'll add it. If it's free software, but you're having trouble getting it installed in our environment, you know something, we can do that too. We can make it available so you can do that parameter sweep. So if you're worried about, software licensing, we can help with that too. And we can point you to places maybe where we can find it. So we have all that stuff ready to go. So the software library is a second unique feature of Flux that is unique compared to most clusters, that you can come in with your problem and we probably have the software to support you. Now you might have heard me mention Exceed earlier. I am the Exceed Campus Champion. So if you notice here, we kind of don't care if you use Flux or not. We want you to use the resource that best fits your need and best fits your computation. We care about computing, we don't care about computers. Yeah, we've got hardware heads around here and they're good at keeping the computers we have because we need them going in an optimal way, but a lot of us are like, something, we will help you with that resource because something that falls into purview of enabling science at the university. So we will help you with that. So Exceed is an example of one of those resources. Exceed, or exceed.org, and because screen sharing doesn't appear to be working today, I'll put the URL down. It's the Extreme Scientific Engineering Discovery Environment. It's a set of resources set up by NSF around the country that you can submit proposals for time on. And the proposals are very simple. You can get a startup allocation. They're only 200, they're up to 200,000 CPU hours, but normally you just need an abstract. So if you've written a paper of work investigated thus far, you can practically copy and paste the abstract with a little bit of editing, and you can get 200,000 CPU hours in Exceed. What's unique about Exceed? So we charge for Flux. Exceed doesn't charge. So you fill out these small proposals and you can get time there. Also, they have machines that are different from Flux. They have something like Blacklight that has a huge memory footprint. I'm talking thousands of gigabytes of memory in a single computer. So you can take probably a problem that you're like, well, I can't do that. It's too big. I can't fit it into memory. If it's even too big for the machines on Flux that have 1,000 gigs of RAM, we can take it over to Blacklight where they have 32,000 gigs of RAM, and we can run, and we can enable work that you probably thought you couldn't do before. We can move it over to a machine on Exceed. So you can do even bigger things on Exceed, both in terms of scale, Blacklight and memory footprint. Stampede has about 10 times the number of CPUs Flux has, so you can run bigger parallel jobs if you need to do that. And through Exceed, we can get you access to something called Open Science Grid. Open Science Grid, or OSG, is really unique in the sense that it really enables that parameter sweep. It's set up for running thousands upon thousands of small jobs, and it spreads them around volunteer machines all around the country that are professionally managed to enable these many small cases. So if you have a whole bunch of signals and you want to evaluate a bunch of different points in the frequency spectrum on those signals simultaneously, farm them all out. Something you may think of as a large single job, you might be able to think about re-architecting it a little bit such that it's many smaller jobs, breaking it up along frequencies, breaking it up along gene snippets, breaking it up along different permutations. And instead of running one big case that walks through them, run many cases that takes one chunk of that. Put it on OSG, and you can have many thousands of processors working at once, and it costs you nothing. So there's different resources out there that are available. We've also since been working on enabling the use of Amazon. I don't know if you've heard that Amazon is now a service that you can pay for at the university with a short code. So if you're using Amazon and you're paying for it off your personal credit card and doing reimbursements, talk to us. We can help you move over as a researcher to using a short code to pay for it, keeping all your existing Amazon images and everything like that. But if you also have something that you think Amazon would be a good use for, that's one of the resources in our portfolio we can help you with. So that is kind of our big swath of resources we help you with. Our most common one is Flux, after that Exceed, after that Amazon. But again, we can help you with other things. And many of the people who are on the email list are right in your unit. Remember, Med, LSA, SPH, etc. They can actually help you with things that those individual schools and colleges have. And we will help you with pretty much anything. So moving data to, if you get a NASA award and you're given time on a NASA supercomputer, you need to move a bunch of data there, we can help you with that. We're familiar with efficient ways of doing that. So that's what I had on that. Please put any questions you have. Dan and I can answer them. You can put them in a chat box, or you can send them in the Q&A area. Anything you want me to cover, go ahead and put them in there. If there aren't any questions, I was actually going to, for those who were curious, actually sketch out how a cluster is constructed, and specifically how we've constructed Flux. So feel free to go ahead and ask questions. Okay, feel free to interrupt us at any time if you do think of a question, but I'm going to go ahead and kind of sketch out real quick how Flux is set up. Flux is set up pretty much the same way almost all compute clusters are for scientific computing are set up these days. Specifically, there's two main set of user-facing resources when they think about computing. So we have, whoops, no, it's not supposed to be that. We have login nodes. Sorry, because screen sharing is not working, I can't use my normal sketch tool. So we have login nodes and we have transfer nodes, which is commonly known as FluxExfer. So these are the machines you kind of interact with from the outside world. And we have two login nodes and one transfer node. And so this is where users kind of come in. What we have in the back, though, behind it, this is what actually makes up the cluster. We have many, many of these compute nodes. You have many of them. So these are the compute nodes. I really don't like this sketch tool. So we have many, many of these compute nodes, and so the compute nodes is where everything actually runs. What you don't see normally, but you interact with without realizing it, is that there's something called the head node down here. And I'm simplifying this a little bit, but not really. This is kind of the basics. The head node has the queue. So the head node, so users come into the login nodes, and they submit a job, and the head node keeps track of that job, and the head node has policy. And so the head node is being reported from every one of these many compute nodes we have, and on Flux we have like 1,000 of them. So these compute nodes are all reporting back to the head node their current state, how much memory they have, how many CPUs they have, whether they're up, how much local disk they have. All these things get pointed back to the head node. And so when users come into the login node, and this is where they compile code and do sorts of things, when they come into here and they submit a job, the job actually goes to the head node. And the head node applies policy saying, like, you're from such and such a research group, you have these resources available, and there's a compute node over here that has enough physical resources to run what you asked for. So if you ask for a machine with 16 cores, and this machine has 16 cores free, you submit your job, it goes to the head node, and then the head node sends that workload to that compute node. And that's basically the entire workload. If you think a cluster is complicated, this is the simpleness of it. It's actually quite simple. If you can type the command to run it yourself, and that's what the next webinar focuses on, learning how to use the Linux command line. If you can type the command to get it to run on the login node, or on like login.engine or login.itd or the stats service or any of those things, if you can type the command to make it run, you can make a batch script. Because all we do is, in the batch script, you put in what you would type to run it. You put it into script, you submit it, we then take it to a machine that has idle resources. And this is how we can actually effectively manage 1,000 computers with 12,000 total cores on a system like Flux. You could submit 1,000 one processor jobs, and we have ways to make that easier, but if you actually just submit 1,000 things, they would all go into the queue, and we would farm them out. If there was 1,000 free processors and you had 1,000 core allocation, we would run 1,000 of them simultaneously, all on different machines, making sure that they're always on a machine that's idle. So that's really the basics of the system. So a few other things that's going on here. We do have disk, shared disk, and this is kind of a requirement for making a system work. And this disk is connected to all the compute nodes and login nodes and transfer nodes. So if you move data into the cluster, every computer sees it. And so when you run workload and you submit it and it's ran on one of these compute nodes, it can directly access the storage. Lastly, what we have on Flux uniquely is we have two different networks. We have a slow Ethernet network, which is kind of like your standard, telephone jack looking network that you put on everything. We use that for management and for some small file I/O. And that's fine for most cases. That's just like what you have on a normal system. But we also have, for those of you who are doing both heavy disk access and parallel computing, we have a high performance network called InfiniBand. And I'm just going to call that IB here, just because this sketch software works so poorly. So we have this InfiniBand, and that does two different things. One is for parallel computing. If you're using Ethernet now and you see bad scaling, that is when you use more computers, it slows down, or it only slows up by less than what you would expect. On our system with InfiniBand, I bet you it'll scale significantly better. InfiniBand has 40 times the bandwidth. It's 40,000 megabits. Just 40 times the bandwidth of your normal gigabit Ethernet, and it has a fraction of the latency. And so everything is optimized for doing parallel communication over that. For those of you who aren't doing parallel communication, but you have file access, this disk down here, it is accessed over that InfiniBand network. So instead of accessing disk over a slow 1 gigabit connection, we can actually access it over a 40 gigabit connection. So that's kind of the general structure. So that's really the whole thing. One cool thing we have that a guy by the name of Russell Decima, or otherwise known as Rusty, has done here is he's added a piece of equipment to this InfiniBand network that if you have your own storage, if you have significant I/O needs and you really need to move that data back and forth, yes, our transfer node has 10 gig Ethernet, so you can move data at a gigabyte a second through this machine. But what you can actually do, if you have your own storage, Rusty has this gateway that is being connected this week at 100 gigabits. That's able to move 10 gigabytes a second. So if you have fast storage, that traditionally accessing storage, this is good for like genomics, things like that that are really I/O bound. We can directly access your storage over this InfiniBand gateway, which will let your storage come over this 100 gig backbone that's being put in next week, or this week. So we can move it at 100 gigabits, that's 10 gigabytes a second, all the way to our InfiniBand fabric. And it's connected with 4 InfiniBand connections. Remember, each one of those is 40 gigabits. So we have 4 InfiniBand connections, and then every compute node, and we have 1,000 of them, are connected at 40 gigabits. We can move data off of your storage into our compute nodes probably faster than you can to your own nodes. And that's a way you can actually overflow into our system and get good access to your data. we directly access value storage and a few other things like that. But this is actually a cool thing that we've done to be able to really enable your storage to come to our system really effectively. So that's everything I had. That is basically the structure of Flux. I didn't get into a lot of the details about how the queue is actually set up. So if you want to know that, you can go ahead and ask that question. But otherwise, I won't bore you with it. But again, you can contact us at hpc-support@umich.edu. This is being recorded and will be posted at our YouTube channel, which is a link down there at the bottom. But our username is UMCoECAC, which you might recognize as our old name. Again, anything you're doing with computation on campus, please contact us before you get too far into it. We're more than happy to answer your questions. You're not inconveniencing us in any way. It's what we're here for, to help you out with. And we'll recommend you the best resources in terms of hardware, software, data management, data transfer, things like that. So any questions? Oh, okay. So what's the difference between a node and a core? Okay, here, let me actually sketch that for you. How do I get a new whiteboard? So yeah, this is actually a common confusion. And so here's what a node is. A node is an individual server. It's a single machine with a network connection and some local disk. And it contains, on Flux, but it's different on every machine. Flux, the common node, has 2 processor sockets. And then these sockets have 1 or more cores. So in this example, I'm going to say each socket has 8 cores. So this is a 16 core node. This is kind of like the unit you buy. So if you buy a processor, like my laptop I'm showing this presentation off of, it has a dual core processor with hyperthreading. So it shows up as 4 cores. On high-performance computers, you pretty much always turn off hyperthreading, and they are off on our system because those 2 cores are fake. They actually sometimes slow things down for computationally heavy stuff. So I have 2 physical cores. Now, what can I do on each core? Each core can run a thread of execution. So, for example, if you take R out of the box can only use a single core. So if you have a 4-core workstation and you're running R simulations, you should actually run 4 copies of R at once. Each one of them will run on a core. Because a core really is what was back in the day a processor. It's a single thing that can run a thread. Having a 4-core box to run 1 copy of R faster, you will find will be no faster than a single core box with that single core being identical. Because the other 3 cores in your 4-core processor aren't doing anything. Because a core has a thread of execution, you need to have multiple threads of execution going. And so if you're doing a parameter sweep, you can just run 4 parameters at once. And there's tools inside R to make that easier. I'm just using R as an example. Every application pretty much has some sort of tool like this that you can take advantage of more processors. But really a core is a processor, and a socket holds multiple cores, and a node holds multiple sockets. So a node really is a physical computer, and a core is an individual execution unit inside that computer. So in this example, with this 16 core node, I could run 16 copies of R, and they would each get 1 core and run at optimal speed. If you have an MPI code, it can run 16 MPI ranks. If you have a threaded code, you could run 16 threads of that shared memory code. So does that make sense, Jordan? Does that answer your question? Okay, so now your next question, what is the basic units of purchase and access on Flux? A unit of access on Flux is 1 core for 1 month. This is your building block. So the smallest you can get out of this 16 core node is 1 of the 16 cores. So 16 core node costs, say, $5,000. That's about what a 16 core node with 64 gigs of RAM costs. On Flux, you get 1 core for 1 month. Oh, and this also comes on Flux, on standard Flux, with 4 gigabytes of memory. So this is your purchase unit. This, for the 3 big schools, is $6.60. Get my decimal here. This is the building block, and you can stack them. And so you get them in multiples. You can get 16 cores for 1 month. Well, the price for that is 16 times 660. And you can add cores at any time. You can add cores at any time. So if you start with 1 core and you find that you want to add a few more, we can add them. There's other products than standard Flux. So this is standard Flux. This is the most popular one. Standard Flux has nodes that look like this: 2 processors, 2 sockets with multi-core processors, and they come with 4 gig of RAM each. This is 660. There's also large memory Flux, which has 4 socket nodes, and they have 32 or 40 processors, sockets, cores total. So you have 4 sockets with 32 cores, and they come with 25 gigs of RAM for every core. So those machines have up to 1,000 gigs of memory in a single node. So if you have something where you don't need as many cores, but you need more memory, we have that. We also have GPUs, and we also have PHYs. And those all have their own price depending on what it costs us to acquire them. So standard Flux is the most popular. When we say Flux has 12,000 cores, it's 12,000 standard cores. Large memory Flux, I think, has 360 cores. It's 10 nodes with 1 terabyte of RAM each. We have 10 terabytes of RAM in large memory Flux. We have 40 GPUs, and we have 8 Xeon PHYs. So that is kind of like the unit. Everything is a core month. Everything is a core month. So you rent things by the month, and you can start them at any time. So today is the 28th. If you asked for an allocation to start at midnight, the 29th, it would run till the 29th of the next month. And if you ask for 6 months and you find out you only need 3 or you want fewer cores, we can cut it off at the month boundaries. But right now, everything has to be by the month. So that should answer your question in terms of what's available now. So we have the different products, and they're all by the core by the month. And they come with different amounts of memory and different attached features. There is a coming product that we hope to have sometime this calendar year. Something called Flux on Demand, which works more like Amazon. We don't guarantee that the resource is available, but we only charge you for what you submit. So instead of being by the month, it's by the consumed core second. So if you submit a 100 core job and it runs for an hour, well, it'd be 100 cores times 3,600 seconds, and we would figure out what this 660 is in seconds, and we would multiply it out, and we charge you only for that. There's a difference between that and standard Flux. Standard Flux, it's more like you leased a core. That 660, it's always there. We guarantee that you can access it. With Flux on Demand, it's going to be full, so depending on what you need. The next question was, what is the basic unit? So Dan included a link to managing a Flux project, which has all this information about how allocations and stuff work, where you can stack cores and get different groups of cores for different users and things like that. It's a very flexible system. If you have questions about how you'd like to do something, you can just send us an email with your specific situation, and we'll give you an idea of how we would create a system for that. Rule of thumb for determining the number of processors to request for a given job. There really isn't. It depends on your code. It depends how your code interacts on our system. It depends what you can take advantage of with your code. really, Kyle, what I would do is send us an email at hpc-support@umch.edu. Tell us the code you're using and what you're trying to accomplish, and we can give you a better idea for that code. But really, you're going to have to do some testing, get an idea of how it scales at different sizes, and then maybe adjust your CPU count. Or instead of running one big parallel job, if it's a parallel capable code, you run two smaller parallel jobs that, while the smaller job may take longer to run, if it's 80% efficient on all those processors, running two smaller jobs at 80% efficient, they both will get done before running one big job that runs at, say, 30% efficient. And we see this sort of thing sometimes. If you use a lot of processors, you can get really low efficiencies depending on the code. And then you have to run a second 30% efficient job after that. Waiting for both of them to get done will take longer than running two of them, even though the individual two running simultaneously, getting the first case done will take longer. I have a question regarding Exceed. What is the number of computing units we have there for free? For example, right now I'm using 300 cores in Flux. Can I expect that much power on Exceed too? So Exceed allocates their resources a little bit differently. Exceed works more like a debit card. Oop, that didn't do what I intended to do. Exceed is always free, but it's free in the sense that you submit a proposal and you get time and you don't ever pay them money. So there's still a cost to doing it. You have to fill out these proposals, but these proposals are really easy and almost all of them get an award. You can get a startup allocation, which is up to 200,000 CPU hours. So notice it's CPU hours. So on Flux, you kind of set aside these cores, right? On Exceed, instead, you get something called SUs. And they're a debit card. Every resource on Exceed has their own limit, but example, on Stampede, you can submit a 4,000 processor job as long as it uses less than the number of CPU hours you have allocated to you, you can run it. So you can run it any way you want. You can run single node jobs. They take 16 SUs per hour because there's 16 core nodes. If you ran a 1,000 core job, you'd run through 1,000 SUs per hour because you're running 1,000 processors for an hour. So they work more like a debit card. So this is a lot like what Flux on Demand will be. So Exceed's a little different. If you have a 300 core allocation on Flux right now, those 300 cores are always there. You can't go over 300, but you can submit a job and they're always there. And you can run on there all the time. On Exceed, if you had 300 core months of time, you figure out the number of hours that is, you just submit jobs into their system, and when it runs a job, it just deducts the time that it ran for. So you can run bigger jobs on Exceed, but you may run down your 300 core months sooner. Does that make sense? It's a debit card more. So it's less like you own the machines and more that you're just waiting in line with everybody else. So we see Flux and Exceed being complementary. Flux, because of the guaranteed access, gives you quicker turnaround time for access, so it's great for doing development and things like that. But when you got a lot of stuff to run, you get a Exceed allocation, put them all in their queue, and they will run it when they can, and you can use more cores for a single job, but you don't lose anything when you're not running. So that's the difference. So it's a little different, and that's why we see them being complementary. That answer your question, Theo? Okay. If you have more questions about the specifics of Exceed, send in a question to HPC-support, and I'll get something to you based on your specific situation, what you want to accomplish. But again, I'm the Exceed Campus Champion, so I'm your local support for Exceed. So I'm your advocate and support. I have access to all the machines. I'm familiar with the machines. I can give you both technical support and administrative support. Any other questions? Okay, again, we are recording this, so this will be posted. Follow-up, so there's a PBS Basics on Friday, and Linux Basics on Wednesday. So Wednesday, 10:30 to 11:30, we have basic Linux commands. So if you're unfamiliar with Linux commands, come back to the same place on Wednesday, and we'll cover like how to get around on Linux, you know, ls, pwd, how to get around with Linux for those of you who are new to it. And then Friday, same time, we're going to cover PBS, which is the batch system, how to use the cluster specifically, and modules, which is how to use our software library. So we'll cover stuff that's specific. We'll use Flux as an example, but Exceed also uses batch systems like PBS and modules for getting access to the software. So if you get familiar with ours, if you go through our training, you'll be able to go to a different resource and you'll be able to get moving faster because you kind of already have an idea of what it's supposed to do. So again, thank you, and the place to always ask questions is hpc-support@umich.edu. I'm glad you found it helpful. No problem. We have a bunch of old ones on the YouTube page, so you can find those. Some of the information could be a little out of date because we do it as specific to the time it was done. But you know, if you want an update on a webinar, please let us know and we'll just run it again.